So we know about the vector product of two vectors, right? So now we'll talk about the linear velocity and angular velocity. Let us consider a disk. Okay, let's consider a disk which is rotating about some axis. Okay, let's suppose we have this disk and it is rotating about this vertical axis which passes through its center. Okay, so let's suppose this is the origin of coordinate system. Okay, and this disk is rotating about this vertical axis which passes through its center, O prime. Let's call it O prime. Okay, so now let's consider a point on this disk. Let's consider this point. So since this disk is rotating, this point will perform circular motion, right? So it will have some linear velocity and some angular velocity. Okay, it will have some linear velocity, some angular velocity. So angular velocity will be in what direction? We know that we have to use which rule? Right hand thumb rule. Okay, if the particle is moving in some direction, okay, it is moving in circular motion, then we have to curl our fingers in direction of motion of particle and stretch the thumb. So the angular velocity will be vertically upwards if this wheel is rotating in anti-clockwise sense, right? Okay, so omega is vertically upwards. So when this point, when this particle is at this position, okay, it is performing circular motion, and when it is at this position, its linear velocity will be directed in tangential direction. Okay, it will be directed like this, tangential at this point, v bar. Omega bar is directed vertically upwards, right? So now let's suppose the position vector of this particle is given by this vector. Okay, so this is, I'm sorry, so this is, let's call it r bar. Okay, this is r bar. So we can resolve this position vector along two components, right? So one component will be like this. So let's call this component as r parallel to this axis. So r parallel, and this component, there will be other component as r perpendicular. All right. So we have this disk which is rotating about this vertical axis. Okay, this vertical axis. So its angular velocity is omega bar, right? Its angular velocity is omega bar. Okay. So now it has got some linear velocity also. So linear velocity will be what? It will be in tangential direction. It is in tangential direction. Okay. So now we want to find out the relation between this linear velocity and angular velocity. Okay. So both are vector quantities, right? So now the relation will involve a vector product of two vectors. Okay. So let's see. So now what I will do is I will find out this product, omega bar cross r bar. Okay, let's find out this product, omega bar cross r bar. So omega bar is directed vertically upwards. Why? So it is right hand thumb rule. Okay, our particle is revolving in circular motion. So we curl our fingers in direction of motion of particle and stretch our thumb. Our stretched thumb gives the direction of angular velocity. Okay, so omega bar is directed vertically upwards. And r bar is position vector of this particle, right? So this r bar we can represent as this vector o prime, we can say, plus this vector. which is directed from O prime to P. Okay, so we can write this as omega bar cross this vector O prime bar plus OP prime bar. Okay, this is equal to omega bar cross O prime. I am calling R parallel. O prime P I am calling not OP, it is O prime P. Okay, I am calling it R perpendicular. What is parallel and perpendicular? So R parallel is a vector which is parallel to this axis, or which is parallel to omega bar, you can say. And R perpendicular is a vector which is perpendicular to the axis. Okay, so this is R parallel plus R perpendicular bar, right? So then what will be the cross product of omega bar and this vector? This you can tell me. What will be cross product of omega bar, which is directed vertically upwards, and this vector which is also directed vertically upwards? See, omega bar cross R parallel, it is equal to, let's find out its magnitude. So it is magnitude of omega, magnitude of first vector, multiplied by magnitude of second vector, multiplied by sine of the angle between two. And how much is the angle? Angle is 0, and sine 0 is 0. That means this product is 0, right? And then we have the second product, omega bar cross R perpendicular bar. What will be its magnitude? It is magnitude of first vector, which is omega, multiplied by magnitude of second vector R perpendicular, multiplied by sine of the angle between two. And what is angle? 90 degrees. Okay, sine 90 is 1. So this is equal to omega multiplied by R perpendicular. So then this thing will be equal to what? So its magnitude is equal to omega multiplied by R perpendicular. Okay, so omega bar cross R bar, its magnitude is equal to what? Omega multiplied by R perpendicular. So question is, what will be its direction? What will be its direction? So see, if you use right hand thumb rule, okay, we are doing vector product. So omega bar is directed vertically upwards. This R perpendicular, it is directed towards right. So if you do omega bar, okay, which is upward, cross, okay, this second vector which is directed towards right. Can you see this? Yes. Okay, so this vector cross this vector. So your straight thumb, it is perpendicular to this vector as well as this vector. Okay, and it will be in this direction. Okay, so you can see this tangent at this point. Tangent is perpendicular to radius, right? Tangent is perpendicular to radius. Okay, and it will be perpendicular to this vertical line also. Okay, it will be perpendicular to omega bar also. So if you do omega bar cross R perpendicular, you will get this direction. You can check that using right hand thumb rule. Okay, so put your right hand in direction of omega bar, curl your fingers towards the second vector and stretch your thumb. So your stretched thumb shows this direction. Okay, which for me is this direction. So are you getting this? It will be directed along V bar. Okay, and you can see this magnitude. Okay, this magnitude omega multiplied by R perpendicular, it is equal to V, magnitude of V bar, because in circular motion V is equal to what? R times omega. That means radius multiplied by the angular speed, right? Linear speed is equal to radius multiplied by angular speed. We have studied this in circular motion, right? So here radius is this R perpendicular. Okay, so this thing is equal to what? This I'm sorry, this thing is equal to what? This thing is equal to V bar. So V bar is equal to omega bar cross R bar. Okay, so this is true for rotational motion. Okay, this is true for rotational motion. See here, this object is performing rotational motion about a fixed axis, about a fixed axis. Okay, so then in that case, the linear velocity of any particle on that object will be equal to what? It's omega bar cross its position vector. Okay, omega bar cross its position vector. Got it? Yes, no? You can see here that if we do this product, omega bar cross r bar, it is equivalent to, okay, omega bar cross r bar, it is equivalent to omega bar cross r perpendicular bar. So r bar is equal to this r parallel bar. This r bar is equal to r parallel bar plus r perpendicular bar. Okay. So this first cross product is equal to 0. That means omega bar cross r bar is just equal to what? Omega bar cross r perpendicular bar. Okay. So if we just think about circular motion. Okay. Let's suppose we have particle which is performing circular motion. So this is the particle. Then if I find its position vector with respect to this origin. So now which is r perpendicular, the vector which is r perpendicular in this previous diagram, I am going to call it r bar here. Okay, because I am going to measure position with respect to the origin of circle. So in case of circular motion only, where we are measuring the position with respect to the center of the circle. Okay, so where radius vector is your position vector. Okay, in this case, again the angular velocity will be directed like this. If it is performing circular motion in anticlockwise sense, the angular velocity will be directed vertically upwards like this. This is omega bar, and the linear velocity will be directed in this direction. Sorry, it's v bar. Okay, so here what will be the relation between v bar, omega bar and r bar? So v bar will be equal to what? It will be omega bar cross r bar only. Okay, so now sometimes there is a question that there is a particle performing circular motion. Okay, what's the relation between v bar, omega bar and r bar? So this is the correct relation. Okay, this is the only correct relation. There would be one option like this: v bar is equal to r bar cross omega bar. Okay, which is of course not correct. Okay, this is not correct, right? So we have to remember this relation: v bar is equal to omega bar cross r bar. Okay, we'll talk about analogous quantity of force in rotational motion, and that quantity is known as torque. Okay, so what is torque? So for an example, let's suppose you open or close the door of your room. Okay, any room. So where do you exert the force? So of course, if door is closed or door is open, you want to close it, you will need to exert some force, right? So do you exert the force near the hinge? Of course not. So let's suppose we have this door and the hinge is over here. Okay, this is the axis about which it will rotate. Okay, it will open or close, right? So do you exert force here? No, you exert a force here. Okay, so there will be a handle like this. Okay, so holding that handle, you will open it or close it. Okay, so that handle would be very far away at the other end, you can say, of this door, nearly at the other end, right? It's nearly at the other end. Why so? Why that handle is not here? It's because as you move closer and closer to that hinge, you will need to exert more force. Okay, you will need to exert more force, right? So now let's suppose, let's consider some origin here. So I will consider the origin as the midpoint of that axis or the door, you can say. Okay, so this is my position vector. Okay, so this is my position vector. So let's suppose this is the point where I am going to exert the force. Okay, so this is my r bar. Now we can see that when the force is exerted perpendicular to the door, okay, when you the door is like this, okay, the door is like this. When the force is exerted perpendicular to the door, then the rotational effect is maximum. It's easy to rotate it, okay. And when the force is exerted parallel, can you rotate it applying force like this? No, right? So when the force is perpendicular to this r bar, okay, then the rotational effect will be maximum. So when you exert a force like this in perpendicular direction only, okay, in perpendicular direction, so opening and closing is easier, okay. If you pull it like this in this direction, if you pull the handle like this, it won't open or close, right? So for maximum effect, what is the angle between the force and this r? It's 90 degrees, right? It is 90 degrees. And that means the quantity which will measure the rotational effect, okay, it is directly proportional to r, okay. So as far you are from the hinges, the rotational effect will be more, okay. So if distance from hinges is more, the rotational effect will be more, right? So it is directly proportional to r. It is directly proportional to force. More force you exert, the rotational effect will be more. And it is also proportional to what? Sine of the angle. Why sine of the angle? Because when the angle between r and f is 0, there is no rotation at all. And rotation is very easy when the angle between r and f is 90 degrees. Okay, see, so sine of 0 is 0. So if r and f are in same direction, then there is no rotation, right? So sine 0 is 0. Okay, so we can say the rotational effect, it's directly proportional to what? R, f, and sine of the angle between r and f. So that angle is theta. Okay, so the measure of rotational effect is torque. Okay, what is torque? Torque is the measure of rotational effect. Torque is the quantity which governs the rotational motion. Okay, so that torque is defined as the magnitude of torque is given as r multiplied by f multiplied by sine of theta. Okay, where theta is the angle between r and f. Now this tells you that this would be a vector quantity, because what is r times f multiplied by sine of theta? It's the magnitude of vector product between what? R and f, right? So torque would be what? Torque is vector product of r and f. Okay, torque is vector product of r and f. Got this? Yes, no? So torque is the vector product between the position vector and the force. Okay, then we'll define one more quantity. So now this torque is the rotational analog of force. Okay, so just like we need force to change the state of linear motion, to change the state of rotational motion, we need torque. I mean, we need force only, but how and where we are exerting that force is an important thing, right? So this quantity is important, basically. Cross product of position vector and the force. This will determine how much is the rotational effect. Okay, so torque is analogous quantity of force in rotational motion. Okay, so now we got a quantity which governs the rotational motion, and that quantity is called as torque, right? So quantity which governs the linear motion, that means the quantity which changes the state of linear motion, is force. So just like that, quantity which changes the state of rotational motion is torque. So we can say if there is no torque acting on a body, so if body was at rest, if body was not rotating, then it will not rotate. And if body was rotating with some angular velocity, it will keep on rotating with that angular velocity. So to stop the rotation of a body also will need a torque. So just like we have this quantity torque, which is analogous of the force in linear motion. So we need a quantity which determines the state of rotational motion. So which is the quantity which tells you about the state of linear motion? What is the measure of motion of a body? This was a question in worksheet. Which quantity gives you which quantity gives you the measure of motion in a body? Is it the mass? Is it the velocity? Is it the momentum? Is it the force? I guess these were the options. What is Newton's second law? Rate of change of which thing is equal to force? Momentum, right? So what is measure of motion in a body? It's momentum. So there is an analogous quantity in rotational motion to the momentum, and it is known as the angular momentum. Okay, it is known as angular momentum. Before that, one more thing, the torque is also called as moment of force. Okay, so sometimes we'll call it torque, sometimes we'll call it moment of force. So torque is also called as what? Moment of moment of force. Okay, then so angular momentum is the analogous quantity of linear momentum. And what is angular momentum? So for a particle moving with velocity v bar, the angular momentum is moment of linear momentum. Okay, how do we define angular momentum? So angular momentum is equal to moment of linear momentum. Okay, so angular momentum is denoted by letter L. So for one particle, let's denote it by a small l only. So L bar is equal to what? R bar cross P bar. So if you have some particle, okay, so let's suppose this is the coordinate system. Let's call it xy. This is x coordinate, this is y coordinate, and the particle will move on this xy plane only. Okay, so the particle will move on this xy plane only. So particle is right now, there is this particle which is right now at this position. So let's call it r bar. Let's call this position r bar, this position vector. And suppose it is moving in some direction. Okay, so let's suppose it is moving in this direction. Okay, in this direction with some velocity. Okay, so it will have some momentum in this direction, right? So p bar is its momentum. So how do we define what is p bar? P bar is m into v bar. How do we define its angular momentum? So it is r bar cross p bar. It is r bar cross what? P bar. Okay, right? Then see what's the connection between torque and angular momentum. Okay, so we'll see that. So what's the connection between force and linear momentum. Force is rate of change of linear momentum with respect to time. The same is the relation between torque and angular momentum. We'll see that. So for that, let us take derivative of angular momentum with respect to time. Okay, so taking derivative of angular momentum with respect to time, what do you get? So it's dl bar by dt, okay, and it's equal to d by dt of r bar cross p bar, okay. So which is sorry, dr bar by dt cross p bar plus r bar cross dp bar by dt. So this is product rule of derivative, right? If you have product, scalar product, vector product, doesn't matter. If you have product of two quantities, so what is derivative of that product? It's derivative of first quantity multiplied by second quantity as it is. So derivative of first quantity multiplied by second quantity as it is plus first quantity as it is multiplied by derivative of second quantity. Okay. So then what is dr bar by dt? So this is rate of change of position with respect to time. So this is velocity, right? This is velocity of a particle. So we have v bar cross p bar. Okay. And what is p bar? P bar is equal to m times v bar only. Okay. Plus what is dp bar by dt? Rate of change of momentum with respect to time. Very good. So it is force acting on the particle. So this thing is r bar cross f bar. What is v bar cross v bar? Then it's 0. Okay. The cross product of a vector with itself is 0 because angle is 0. Okay, its magnitude will be v into sine of 0, right? So this thing is 0 and this thing is torque. So this thing is second term is torque. So see, what do you get? If you take dl bar by dt, you get torque. Okay. So this is, can you see, this is analogous to this law, Newton's second law, okay, which is F bar equals to what? dp bar by dt, right? The rate of change of momentum with respect to time is the force. Okay, force acting on a body is equal to what? The rate of change of momentum with respect to time. Okay, so just like that, so just like force governs the state of linear motion, torque governs the state of angular motion or rotational motion. So torque is analogous quantity of force. And now can you clearly see that analogous quantity of linear momentum for angular motion or rotational motion is angular momentum. Okay, circular motion you can say, circular motion, angular motion, rotational motion. Analogous quantity of P is L. And this is, what is this then? This is the Newton's second law. This is Newton's second law. For which motion? For angular motion or rotational motion you can say. So is this thing clear? Have you understood that this is how this is analogous quantity of momentum? So alright, so this is for case of one particle. Okay, we discussed the torque acting on one particle, which is equal to what? The rate of change of angular momentum of one particle with respect to time. Okay, so then see, if we have a body, so any body will have n number of particles, right? this body will have n number of particles. So let's suppose this body rotates about this axis. Okay, there is some origin and there are n number of particles within this body. Their masses are m1, m2, m3, so on and so forth. So when the body rotates, all these particles will perform circular motion, right? This particle will revolve in this circle. Let's call its mass is m1. For this particle, let's suppose it is m2. So the radii of circles will be small, okay, some will be large, right? But which thing is true, that all the particles they move through same angle in same amount of time. That means their angular velocity is same, right? So this is m2, okay. So there are n number of particles in this body, okay. So if you add up angular momentum of all those particles, what will you get? So you will get angular momentum of body. Angular momentum of the body, we'll call it capital L, capital L bar. It is equal to sum of angular momenta of all the particles within the body. So it is L1 bar plus L2 bar plus so on and so forth up to Ln bar, right? So then now if you take derivative of this angular momentum with respect to time, it is equal to derivative of dl1 bar by dt, okay, plus dl2 bar by dt plus so on and so forth up to plus dln bar by dt, okay. And this thing again by the same argument, by this argument only we can say it is r bar, r1 bar cross f1 bar, okay. So it is r1 bar cross f1 bar. What is f1 bar? F1 bar is force acting on first particle, plus this will be r2 bar cross f2 bar, okay. This is force acting on second particle, plus so on and so forth up to plus, okay. We have rn cross fn bar, okay. So now force acting on a particle can be an internal force, it can be an external force, right? So f1 bar is equal to, we can say, f1 internal plus f1 external, right? So this is the torque, okay. Torque acting on first particle, this is torque acting on second particle, this is torque acting on nth particle. Cross product of position vector with force is torque, okay. So now whether the internal force contributes to torque or the external force only contributes to torque is the question. So answer to this question is only the external forces, okay. The external force acting on body contributes to torque, okay. So what could be the reason of this? So see, the reason is, if you see Newton's third law, okay. So for an example, let's suppose we have two particles, okay, inside the body. This is m1, this is m2. The force between these two particles, let's suppose the force acting on first particle due to second particle, it will act along this line, okay. It will act, I'm sorry, it will act along this line. So this is F12 bar, force on 1 due to 2, and force on 2 due to 1 will also act along the same line like this. The two forces will be equal and opposite. But see, we are not adding the forces here. What are we adding? We are adding the torques. Okay, so now you can say there would be some torque. There would be some torque due to the external force. There will be some torque due to the internal force. Okay, so what are we? Sorry. So what are we discussing? We are discussing the torque due to the internal force. So see, now if you see the position vector of this first object with respect to the second object, okay, so this force acts in the same line as that of the of position vector of one object, not object. If you look at the position vector of one particle with respect to the other particle, what will be that position vector? So if we see position vector of m1 with respect to m2 will be this one. Okay, you can call it r12 bar, right? This is r12 bar. Okay, so now the position vector is directed like this. So force due to the second particle on the first particle, it is acted in the same direction as that of the relative position vector of this particle with respect to this particle. So what will be torque? You can say torque about this point will be what? It will be r12 bar cross this f12 bar, and that will be equal to what? 0. Okay, that will be equal to 0 because the position vector and the force, they are in same line. Okay, so which force are we talking about? The internal force. Okay, so what does that mean? It means that the contribution of internal forces to the torque is equal to 0, and the torque is only caused by external forces. Okay, so torque is only caused by what? External forces. So what is dl bar by dt? So it's equal to r1 bar cross f1 external only, plus similarly it is r2 bar cross f2 external, the external force acting on second particle, plus so on and so forth up to plus it is rn bar cross fn external. Okay, so this is torque on first particle, this is torque on second particle, so on and so forth. So we can say this is the total torque acting on body. Okay, so tau bar is tau 1 bar, tau 2 bar, tau 3 bar, so on and so forth up to tau n bar, right? So the rate of change of angular momentum of a body is equal to what? The total torque acting on body. And the total torque on body is due to what? External forces only. There is no contribution of internal forces in this total torque. So is this thing clear? Why is it so? Let us see some problems based upon this topic. Okay, so what is the value of linear velocity if r bar is this, omega bar is this? These are all NEET questions. Okay, so how do we find it? V bar is equal to omega bar cross r bar. So it is equal to what? We know how to find out vector product. So it is determinant of I, j, k. So omega x, omega y, omega z in the second row, and rx, ry, rz in the third row, right? So it is 5 minus 6, 6, 5 minus 6, 6, and 3 minus 4, 1 in third row. So let's solve this. This is simple. This I cap multiplied by. So minus 6 times 1 minus 4 times 6. So that will become plus. So minus 6 times 1 is minus 6, plus you have 24. So that is 18. Right? Minus j cap multiplied by. So this thing multiplied by this thing. So 5 times 1 is 5, minus 6 times 3 is 18. So 5 minus 18 is 13. Okay, minus 13. Plus k cap multiplied by this product. So 5 times minus 4, minus 20, minus, and now this will become plus because we have minus 6. So minus 6 times 3, 18, right? So minus 20 plus 18, how much? 2. Okay, so multiply by 2. So which is the answer? 18 I cap plus 13 j cap plus 2 k cap. It is plus, no? No, it's minus, right? This is 5 times minus 4, minus 20, okay, plus 18 is minus 2. So option B is the answer. Okay, this is straightforward. Everybody? Good. Then, so next question is find the torque about the origin when force of 3 j cap Newton acts on a particle whose position vector is 2 k cap meters. So what is torque? Torque is, it is 6 I cap or minus 6 I cap. Or is R bar cross F bar, right? So see, R bar is 2 k cap. Okay, it is 2 k cap cross minus. Okay, good. 3 j cap. Right? Remember the rule? Good. Okay. 2 times 3 is 6. Okay. And we have this rule. So when we take cross product of I cap, j cap, k cap. Okay. So we draw a circle. Then we mark 3 points like this. If we go in cyclic order, that means from I to j, j to k, and k to I. So I cross j is equal to k. J cross k is equal to I. And k cross I is equal to j. Okay, but if we go in opposite direction, that means if I take j cross I, then it will be equal to what? Minus k. Okay, if I take k cross j, it is minus I. And that's what we have here. K cross j, it is minus I. Right, so this is minus 1 into I cap multiplied by 6. So minus 6 I cap. Okay, so this is the answer, option C. Simple. So this is another question. The moment of force, this is the force, okay, which is acting at this point, about a point, 2 minus 2 minus 2. So now we don't have to find it about the origin. We have to find it about this point. Okay, so let's suppose this is some point. Okay, so let me explain what is the case. This is one point. Okay, let's call it R1 bar, and you are exerting a force at some other point. You are exerting a force at this point. Let's call it R2 bar. This is R2 bar. Okay, so force is acting at this point. Okay, now you are not asked what is the torque of this force with respect to origin. If it was the case, then it is just R2 bar cross F bar. They are asking what is the torque about this point. Okay, so we have to find this vector first. Okay, we have to find this vector first. Anyways, we have to find out this vector, which is R12 bar. So can you say R2 bar is equal to R1 bar plus R12 bar, right? So what will be? See, R2 bar is equal to R1 bar plus R12 bar. This is by triangle law. R12 bar is equal to R2 bar minus R1 bar. Okay, so you are given with the point. So this is R2 bar. Okay, I mean this is the position of R2, this is position of R1. So we can substitute that. So we get R12 bar is equal to what? This 2 minus 2 minus this 2 into I cap plus 0 minus minus 2. 0 minus minus 2 into j cap. Okay, plus it is minus 3 minus minus 2 or minus 3 plus 2 times k cap. So that is 0 I cap. 2 j cap and minus 1 k cap. So now what is torque? It is R bar cross F bar. Okay, it will be R12 bar cross F bar. So let's find it out. So torque is equal to I cap, J cap, K cap. Then R is 0 I cap. So 0, 2 J cap minus 1 K cap. And the force is 4, 5 minus 6. Okay, this is the force. So what can I do? I can make this small. No, there is no option. Okay, so let me add a page. So what do we have? I cap multiplied by this thing into this thing, 2 into minus 6 minus 5 into minus 1. So this is equal to I cap multiplied by 2 into minus 6 is minus 12 minus 5 times minus 1 is minus 5. So minus minus plus. So minus 12, okay, to 5. Then J cap multiplied by we have 0 into minus 6. So that's 0 minus 4 times minus 1. So it is minus j multiplied by 4 times minus 1 is minus 4. And then k cap multiplied by you have 0 times 5 minus 4 times 2 is minus 8. Okay, so minus 8 k cap. So let's check. It is what? Minus 7 I cap. Okay, plus 4 j cap minus 8 k cap. This is the answer. Okay, so minus plus minus. Oh, there is no such option. Did I do some mistake? How come? Yeah, it is minus minus. Okay, sorry. It is minus minus. Okay, that will do plus. Right. So this will be minus. Okay. So then option is the answer. Okay, good, Sanjay. All right. So this is straightforward question. Yes. Then there is another question. Force F bar is the thing is acting at a point. This point. The value of alpha for which angular momentum about origin is conserved is. So when is the angular momentum conserved? So what is rate of change of angular momentum? It's equal to torque. So if torque is equal to 0, if torque is equal to 0, angular momentum will be constant, right? L bar will be constant. That means will remain conserved. Okay, so just like when force is 0, momentum remains conserved. Just like that, if torque is 0, angular momentum remains conserved. So angular momentum will be conserved when torque is 0. That means torque bar with R bar cross F bar is 0. So this is IJK. Then we have R bar is 2 minus 6 minus 12. So 2 minus 6 minus 12. Alpha 3, 6. Let's solve this. So what we get? We get that I cap multiplied by 6 times minus 6 is minus 36. Minus 36 plus this 12 times, okay, t. This is also, but this will be positive. Okay, so I cap multiplied by minus 36 minus minus plus 36. So this will be 0 plus have j cap times what is 6 times 2. Okay, plus minus j. So minus j cap times 6 times 2, which is 12, minus, okay, minus 12 times alpha. So that is plus 12 alpha. Okay, and then you have one more, that is plus k cap times 3 times 2, okay, plus 6 minus minus, okay, minus 6 times alpha, that is 6 alpha. And for conservation of angular momentum, this thing should be equal to 0. So that means all the components of this vector torque should be equal to 0, right? So you can pick this component or this component involving alpha, right? So 12 plus 12 alpha is equal to 0, or you can say 6 plus 6 alpha is 0. That means alpha is what? It is minus 1. Okay, since 6 plus 6 alpha is equal to 0, it means 6 alpha is minus 6. So alpha equals to what? Minus 1. So this is the answer, option C. So let's see next question. When a mass is rotating in a plane about a fixed point, its angular momentum is directed along a line perpendicular to plane of rotation. The line making an angle 45 degree to the plane of rotation, radius the tangent to the orbit. Which is the answer? Right, it is option A. Okay, this is very straightforward. Let's see next question. Again, the next question is similar. Okay, find the torque of a force F bar equals to this thing acting at a point R bar equals to this thing. They are just asking you to do a vector product. Okay, so let's find out torque. It is IJK when 731, okay, R bar and minus 315. This is M. This is equal to I multiplied by 3 times 5 minus 1 times 1. That's 1. So 15 minus 1 minus J multiplied by, you have 7 times 5, 35 minus 3 times 1. So it's minus 3. Okay. So minus minus plus 3. Plus you have K multiplied by 7 times 1, 7 minus 9, that is plus 9. What's the answer? 14 I cap. Then 35 plus 3 minus 3 J cap plus 16 K cap plus 16 K cap. So option C is the answer. Okay. The next one, again the same question. Okay, so let's do one more vector product. What is the torque of this force acting at a point, about the origin? Torque is equal to I cap J cap K cap. Then R bar is 3, 2, 3, 3, 2, 3, and force is 2 minus 3. Right. Then this K cap multiplied by 2 times 4. It's 8 minus 9. Okay, minus 3 times 3. Minus 9. So minus minus plus minus J cap multiplied this times this. So 12. 12 minus 6. Okay, so 12 minus 6 plus K cap multiplied by now 3 times minus 3, which is minus 9 minus 2 times 2, so minus 4. So 20 I cap. Okay. Then minus 6 K cap and minus 13 K cap. This is the answer. Which one? Option D. Right. Option D is the answer. Okay. Then next question. So particle of mass m equals to 5 is moving with a uniform speed v equals to 3 root 2 in XY plane along the line y equals to x plus 4. The magnitude of angular momentum of particle about the origin is, this is the question. This is slightly different, right? So you have a particle which is moving along this line. What's the line? Y equals to x plus 4. Okay, this is 9. Y is equal to x plus 4. So at x equal to 0, what will be y? Y is equal to 4. So at x equal to 0, y is 4, right? So 1, 2, 3, 4 you can say. Okay, this 2, 4. So this will be 1 point. Then you can take some other value of x and find out some other value of y. When you have 2 points, you can plot the line. So the line will look like this. The line will look like this. So how much will be this angle? This angle would be equal to 45 degrees. And why so? The reason is, so see, you can say y is equal to mx plus c is the equation of line, if you remember. Okay, m is the slope of the line. Okay, and how can you find slope of line? By using tan of theta, right? So m is equal to 1 here, tan of theta will be equal to 1. That means theta is 45 degrees. Is it clear? Okay, everybody. All right. So the particle is moving along this line, and you are asked what will be its magnitude angular momentum. So think, when particle is at this point, what will be its position vector? Its position vector will be this one. Okay, so it is just force j cap, you can say, right? What is position of this point? 0, 4. Okay, x coordinate is 0, y coordinate is 4. So position vector is 4 j cap. And then this line, it is moving along this line. So its velocity or momentum will be directed along this line. What's the angle between these two? So this is r bar, this is p bar. What is the angle? R bar is directed like this. Angle is 45 degrees, right? So what will be? What will be what? Angular momentum L is equal to R. It is equal to, it is R bar speed. And if you want magnitude, is rp sine of theta. Okay, that is r into p into sine of 45. So r multiplied by p is mv multiplied by sine of 45 degrees. Put the values. How much is r? Magnitude of r is 4. This is 5 kg. Speed is 3 root 2. And sine of 45 is 1 upon root 2. This thing get cancelled. Root 2 and 1 upon root 2. There is 5 times 3. 15 times 4. 60. Okay. 60 the answer. Questioning. Particle of mass m moves in xy plane with a velocity v on straight line AB. The angular momentum of particle with respect to origin O is LA when it is at A and LB when it is at B. Then LA equals to LB. Relation between A and LB depends upon the slope line LB. Then LA is greater than LB. LA is greater than LB. Which is the answer? There is a particle which is moving with velocity v. Okay, along some straight line AB. Is there a force acting on this particle? Yes, no. Is it given that there is some force acting on particle? Not given, right? There is no force acting on this particle. It is just moving with some velocity. So how much would be the torque acting on particle if there is no force? Torque will be 0, right? Okay. So if torque is 0, what happens to the angular momentum? it remains constant, right? So angular momentum at point A will be just equal to angular momentum at point B. Okay. So angular momentum does not change. It remains constant if there is no torque acting on the particle or body. Got it? Okay, good. Next question. Small mass attached to string rotates on frictionless table. This mass rotates on frictionless table as shown. If tension in the string is increased by pulling the string, causing radius of circular motion to decrease by a factor of 2. Okay, so radius is decreased by a factor of 2. Kinetic energy of the mass will. So what will happen to the kinetic energy? This is the question. Okay, so see what will happen here in this. Okay, in this question. So you are pulling the string, right? You are pulling the string. So this force will be in direction of radius. Yes or no? When you pull the string, the force will be in direction of radius. Okay. So will there be a torque? No torque, right? Because direction is same, direction of radius. Okay, or you can say position vector of the particle and the external force that we are using to pull the string. The direction is same. So that means there is no torque. Okay, R bar cross F bar will be equal to 0. So if there is no torque, what will remain constant? Angular momentum will remain constant. Okay, so what is angular momentum? That is equal to R into P, you can say. Okay, so for a particle perform circular motion, see R and T bar, R and velocity, they are perpendicular to each other. So how much is angular momentum? So it's R into P multiplied by sine of 90. Okay, sine it is 1, right? Because see, velocity and position vector, they are perpendicular to each other. Okay, so this is just R into P, and P equal to mv. You can see this is mv into R is the angular momentum, and it will remain constant. Okay, so you can say L1 equals to L2. So original angular momentum was L1. Then when he pulls the string, final angular momentum is L2. It is mv r mv1 r1, let's say, not m1, mvr. Okay, but you are changing the radius, so speed will change. Mass of that particle, mass of that uh, mass will remain constant. Okay, so L2 is m, mass will remain constant, p2r. Okay, so m and m gets cancelled, and what is r2? So radius is decreasing by factor of 2. That means it will be r1 divided by 2. Okay, it will be r1 upon 2, right? This thing gets cancelled. So therefore v2 will be equal to times v1. So if v2 is 2 times v1, how much will be kinetic energy? The velocity increases by factor of 2. The kinetic energy increases by factor of 4 because it is directly proportional to velocity square. Okay, so k will be equal to 4 times k1. Which is the answer? It increases by the factor of 4. This is the answer, right?